This is a presentation about horizontal control surveying. As we know, the horizontal control can be achieved using different methodology. In this presentation, we will present to you how to do that using the intersection. So usually the resection and intersection, they are tackled in one subject, but here we will be doing the intersection. But before we go into the intersection, let's just have a small or quick comparison between resection and intersection. Usually in these two methods, which are two specialized forms of triangulations, we will be using 3 control points either for the resection or the intersection. Of course, we can add more control points, but typically in the standard format of this problem, we are using 3 control points. So in the resection, we have the instrument where we will be doing angle measurements. The instrument is installed. It is set up on the unknown points. So we have the instrument set up on the unknown points, so it is accessible and we can occupy it with the instrument. While the control points, they are not accessible for the instrument, and we will be doing the measurements from the unknown point only. What are the measurements? It is the angles. Now, for the intersection, we will do the measurements from the control stations, the 3 of them, to the unknown points. So we have 3 control stations. We set up the instruments. We have access to them, but we do not have access to the unknown point to install and occupy it with the instrument. So the measurements will be the angles from the unknown points to the unknown from each of the 3 control stations. So this is typically the difference between these two methods. So let's start with the introduction of intersection, and we said that we do not occupy the unknown station, but we will occupy only the control points and do the measurements, which are the angle measurements from the control points to this unknown point. We have usually 2 situations, let's say, which is inside the triangle. We have a triangle between the control A, control B, and control C. This is the triangle, and the unknown station may be inside this triangle. Other situation is that when we have the point outside the triangle, so point A, point B, and point C, this is the triangle, and this point P is outside. Of course, the number of measurements, they will be different. So here we will have 4 angles. If we want to set up at A, set up at B, we'll measure 2 angles, C at another angle. So we have 4 angles, while here we can measure 6 angles. Because the measurements are more here, the strength of the solution will be much better though. So this is when the point is inside, this is the typical or the preferred configuration. Now about the order of the surveying, in case we are doing the horizontal control using intersection, it is considered as a 4th order. Are we going to enhance it? Yes, we can even enhance it, enhance the accuracy of the solution from 4th order to the 3rd order by doing a couple of things. First of all, we want to keep the figure, or when we want to select the point, we will keep the figures with angles between 60 and 120. We want to avoid so big angles or so small angles. Then we have to measure more angles. So if you look at this figure here, we measure this angle, but we can add one more angle, which is the outside angle. So exterior angle and the interior angle. The same thing, we can add these, and we can add a measurement here. So this measurement here, when we are doing this measurement, we have a geometric condition, which is theta and the exterior angle, they should sum up to 360 degrees. And also the same thing here, beta and gamma and B from the outside should have 360, and the same thing. So we added more observations, added more geometric conditions, and this is what we are saying. The misclosure, when we are considering every angle inside and outside, interior and exterior, the misclosure should not be more than 3 arc seconds in these 360 degrees. This is the condition. And every time we do the measurement, we do not measure it one time, we measure it 2 to 4 times in the face left and the face right positions. All of that will increase the accuracy of the measured angles and consequently will enhance the order of the surveying from a fourth to third order. Let's summarize. What do we have in the intersection? As mentioned a couple of times now, we have the measurements, which are all the angles from the control stations to the unknown ones. What can we add? We can add the exterior angles with a condition of 3 seconds misclosure maximum. We can add the distance measurements. We can add azimuth measurements, but these are not a must. But this is to enhance. So just measuring the angles from the control stations to the unknown station, this is basically enough for solving the intersection problem. But the more we do measurements, redundant measurements, the stronger the solution will be. What are the controls? The controls are already here. We have 3 control stations that we know their easting and northing coordinates. In other problems in the horizontal control, for example, the triangulation, we need a control point, we need an azimuthal face line and the baseline. There we do not have more than one control station. That's why we needed the azimuth and we needed the length of the line. But here we have 3 control points. The 3 control points, they are enough to define the location and the orientation of the problem. So between one control point and the other, we can calculate the azimuth of the line connecting them and the length of the line. And this applies for any 2 points of these 3 control points. Now, how are we going to do the solution? We have the traditional solution of triangle solutions. We solve the triangles, or we go for the one-step least square adjustment. The triangle solution, it is like a stepwise and a procedural solution based on different theories, based on different methodologies. Sometimes we'll do it from different routes and we will have different answers. The least square, it is one integrated method. We'll get one answer from all the processing and it will give you the best. The shortcoming, or not shortcoming, disadvantage we say for the least square adjustment is that we need always an initial estimates of the coordinates of the unknown points. So the easting and the northing of this point must be estimated or given, or somebody has to get an initial estimates of the easting and the northing of point P. We have many methods we can do that. Mainly maybe the triangle solution. We can start with the triangle solution, get the coordinates EP and NP, but these will not be perfect. The least square adjustment will give us a better solution. So why not go for the triangular solution and then enter these estimated values into the least square adjustment and get a better solution. But anyways, you don't have to go to the triangle solution if you have just any method for doing the estimates. Now, at the end of this presentation, I will show you how you can do for particularly for this intersection problem. It is easy to do the initial estimation. We'll show you that later on. The triangle solution, it's the traditional solution that we have ABC, and these are the coordinates. These are the control stations. They have coordinates which we know. From these coordinates, we can calculate the length A, we can calculate the length B, we can calculate the azimuth of line AB, azimuth of line BC, CB, whatever we want. And as you can see, A, B, C, D are the control points, and P is the intersected point. This is what we call it, which is the unknown point. And we need to calculate the easting and northing of this point. In the field, we measure alpha, we measure beta, we measure gamma, and we can measure other angles here and here and here, and we can measure the exterior angles as redundant. But basically, we need just the angles to the unknown point from these control points. As we said, after we finish the measurements, we have to calculate theta and phi, and to proceed with the sine law and doing the length of x, y, and z, until we will calculate also not only the length of x, y, z, but also we want to calculate the azimuths of line AP and BP and CP, and then we calculate the latitudes and departures, and then add the latitude and the departure of AP to the coordinates of point A, calculate P. So here is the multi-solution. If you could find the length and azimuth of line AP, which is line X here, then we can use it to calculate the coordinates of point B. But also we can find the azimuth and the length of line BP, which is Y, and the azimuth of line BP, and calculate P, and also from C to P. So we have different routes to calculating of course, the errors in the alpha, in the beta, in the gamma. This will lead to a solution of point B different from every line you use. And that's why we try to find another method. And this method is the least square, which is a one-step solution, and it would give us the coordinates of point B, which is the best solution based on the given data, based on the alpha, beta, and these measurements. Now, let's move to the least square adjustment. Least square adjustment, we studied the principle and the system of observation equations and everything. We studied it in many places now, and in the horizontal control for the traversing also. So we will jump into the solution. The solution using the adjust program, and we have to prepare the data in the adjust program format, and based on that we'll put the data in the adjust program and get the results. Now, if you are doing least squares for the any type of triangulation, for the traverse, for the triangulation, for the trilateration, for the resection, for the intersection, it is all similar in the structure of the input file. All what we have for the basic least square adjustment of the in general, when we have the intersection problem, basically we have angle measurements, and that's it, plus the coordinates. So we have the coordinates of the 3 points, the control points, and the measurements, we measure 4 angles, and that's it. We have the approximate coordinates of point P. So basically, this is what we are given: 3 control points, we are measuring 4 angles. And of course, we have to come up with the estimates of the point P. According to the format of the input file for the adjust software, we have to do distances. First, we have the identification line or the title line, and we have the number of distances. In case we have only the distance measurements, so the number of distance measurements, they are zeros. What do we have? We have, for the angles, we have 4 angles. So here in the control line, we have 4 angles. And then azimuths, basically in the original problem of the intersection, we do not measure any azimuths. And we have 3 control stations and total number of 4 stations. What can we add? We add a lot of things. We see it in the next example, but for now, we have to list the number, the coordinates of the control station, This is the estimate of the fourth station, which is the unknown station, and these are the angle observations. As we know, the first angle, we will do it P, A, and B. So this is the angle PAB. So we are measuring this angle, and then A, B, P. So this is the angle, and we will follow these. You have to learn. You have to really master how to name the angles and how to assign it in the data file. You just put these in the data file, give it to adjust, get the results. What is the result? In a horizontal control, we repeated that again and again, is that the result is the coordinate of the unknown point. This is the X and this is the Y, and here is the quality and the standard deviation of the solved point. Always we compare it. I created these examples. Yeah, somebody will ask, what is AutoCAD have to do with this? Actually, I created these problems, these examples, using AutoCAD. So when you are doing that in AutoCAD numbers, they are perfect. So we add here to the measurements, we add some noise, as if we are doing the measurements in the field. And based on that, we will have random errors, and then the solution will be different from every. If you are doing the manual solution of triangle solution, then every route will have a different solution, while using the least square, we'll have always the same solution if we keep the same data collected from the field. So this is the solution. Let's go for a different thing. As we said, you can add more observations. The more the observations, the more the redundancy. So we know the redundancy, it is the difference between the number of observations minus the number of unknowns. Unknowns, we have P, EP, and NP. The more redundancy, the better, the stronger. So instead of just measuring 4 angles here, why don't we measure in the field? Why don't we measure distances, like this distance and this distance? Why don't we measure azimuths of these lines? So all of these measurements will add to the strength of the problem. So in case we decided to add more observations, typically we only have the 3 control points, and these are the 4 angles, the basic 4 angles. What additional observation we have? We have the azimuth of line AB, we have the azimuth of line BC, and these are their values. And also we measure 2 distances from A to B and B to C. Always we should have the approximate coordinates of the unknown point. Preparing the data file is the same, but now we have 2 distances which we observed, and 4 angles that we observed, 2 azimuths that we observed, and 3 control points, and a total of 4 stations. These are, first we list the control station, followed by the unknown station, followed by the distance observation, followed by the angle observations, followed by the azimuth observations. Say here, plus minus 1 millimeter, 0.001. These are the last value here. It is, in the case of the angle, it is in seconds. In the case of meters, it is in distances, this is in meters. In the case of azimuths, this is also in seconds. So prepare the file with the input and then put it in the adjust, get the results out. If you compare, the results are the same. 708,095, so it is exactly the same with the addition. Why is this the same, although we added more observations and with the standard deviations? Because of the new measurements, they are almost perfect, like plus minus 1 millimeter, as if we know the distance. So we know it accurately. So the addition of those accurate measurements, they are they confirm the previous results. Now this is another example where we have also the point outside the intersection problem, and the point here, it is U, the point U. We do not have its coordinates. This is the unknown points. Why this file from AutoCAD? So we have, these are the distances from AutoCAD. These are not calculated in this problem. So here we do not have it. If you want in the original problem, we do not have these, and we do not have the coordinates here, and we do not have the lines, the distances here, unless you measure these. So how can we solve this problem? Typical least square problem. First of all, we have to do something. I will show you how can we get the coordinates of point U, the approximate ones. The other values that we have, they are the control point coordinates. We have 4 angles that we measure, 2 azimuths that we measure, and 2 distances that also we measure. Preparing the file is as every file we did before. It is this number of distances. Yes, we have 2 observations in the distances, and we have 4 angles. We have 2 azimuths. We have 3 control points, and total number of 4 stations. 3 control plus 1 unknown. First, we list the control information, the unknown, initial estimates, the distances, the angles, and also the azimuth. Observations here: 1 second, 15 seconds, 15 seconds, and for the distances it is 1 centimeter. So plug in this file into the least square in the adjust program and get the result. So this is a program, an example. Take the numbers, copy it, paste it in an A.dat, and try it in the adjust program. So these are the results as compared to the perfect AutoCAD file. Now, how can we calculate the estimates of the unknown point? In the intersection problem, this is much easier than in the resection problem. So look, what do we have here? We have, in the intersection, we have point R. Look how easy it is. It's a typical procedure. There is nothing complicated. But we have point R. This is a control point. And we have point S. This is a control point. So this line, which is RS, now, I can find its length, all right, from the coordinates of R. We have it. It's a control point. We know it. So we know also the coordinates of the other point S. So we can calculate this, the length. So once we have the length here, we can also calculate the azimuth. The azimuth we can calculate it, delta E divided by delta N, and take the tan minus 1, and you do the quadrant adjustment. At the end, you will calculate alpha azimuth of line RS, and we have the line. Now, the length of this line. Now, can we, based on the what do we have? We said we have the length here. Then we can take this angle and calculate the azimuth of line RU. How can we calculate the azimuth of RU? We have the azimuth of RS, and we have a counterclockwise angle here. So take the azimuth RS, subtract from it the angle here. This angle is, we have it because we measured it, and then we will get the azimuth of RU. Now, can we calculate this angle? We have it, and this line is unknown, which is RU. We have this angle, and we have this angle. From this triangle, we can just calculate this as 180 minus the other 2 angles. So we have the length of this line and the angle opposite to it, and we have this angle and the unknown side. The length we do not know it. So all what we do is the sine law, the law of sines, and then we can calculate the length of RU. So for now, RU we know its length, RU we know the azimuth. What can we do? we can calculate the departure of this line, and we can calculate the latitude. So what do we have from the surveying course? The easting of point U equals the easting of point R plus the departure between R and U. So you take the R and U departure. How do we calculate it? It is the length of line RU multiplied by sine of the azimuth RU, while the latitude here, it is calculated from the length of line RU, which we calculated previously, multiplied by cosine the azimuth RU. So that's it. We have values. Of course, this angle and this angle, they are measured in the field, and they have random errors. But we used it here to calculate this angle, and when we calculated the RU from these, yes, there will be errors in calculating the RU, but it's very, very tiny errors. That's okay. We just wanted initial estimates of the coordinates of point U. So this is very, very enough, let's say, calculations for the coordinates of point U to start with. So here is what we use to calculate the length of RS, the azimuth of RS, and then we calculate the azimuth of the RU from the RS, this one, and we subtract the angle between the two lines because we are going in the counterclockwise location. This is the final azimuth of the line RU. What about the length of RU? As you can see here, we just have theta 1, theta 2, which are the two angles in that triangle. If you want to go back, and this is what we, let me just remove the, so here we have theta 1, and this is theta 2. So we calculated this angle from 180 minus the summation of, this is the angle at U, it is 180 minus the summation of theta 1 and theta 2. And then using the line RS, which is between the two control points R and S, and theta 2, we calculate the length of the line RU. We have the RU, the azimuth, and the value. So what are we going to do? We will calculate the departure and add it to the x coordinate, which is the e coordinate of point R. And this is the n coordinate of point R, and we add the latitude. Latitude of what? Of RU, and the departure RU, calculated like this. Once we get these are the initial, this is part of the solution of the triangle, but this now is an initial values for the least square adjustment. Take these values, put it there, and things are okay. So for now, these are the what we want to know, or what we want to know about the intersection and the solution. So basically, we have input, and we have least squares, and we have initial estimations of the unknown point.